Hi there, this is Courtney and Emmy, and this is our presentation 8 on the second half of Chapter 7. So, Chapter 7 talks about simulating a GG1 queuing system using this three-phase method. And so, there's some pros and cons with this method. It's not the most efficient method, and it involves kind of a lot of redundancy in the program logic, but it's super easy. It's a super easy way of programming and visualizing the structure of a discrete event system, so that's the one that the book decides to use. So with this, we have a few terms that we'll go over. We have an entity, an attribute, event, and list. And so an entity is a component part of a system. So this could be a customer who will enter and eventually leave the system. And then it'll have an attribute which describes some aspect of the entity. So this could be static or dynamic. And so our example of that is that we have an aircraft and the number of seats on the plane is static because that's set, but the people that are occupying them changes, so it'll be dynamic. So then we have event, which is an instant of time at which one or more state changes take place. And so events are instantaneous, but activities have duration. So example could be a customer may finish the activity of queuing and then start the activity of service. And then finally we have a list, which a list is an array used for storing entities and their attribute. So an example of this is a queue of customers waiting for some facility to become available. So next we have steps A, B, and C, and these occur at each event. So A, it's the time advanced from one discrete event to the next, and it's performed by keeping a list of scheduled or bound state changes. And then B, it's the execution of bound state changes, while C is execution of conditional state changes. So in A, a timing routine scans the list to find the smallest time and then advances the variable representing the present simulation time or clock to the smallest time. Then in B, those state changes that are bound to occur at this new time are executed. And they're bound to occur in the sense that their occurrence is not conditional upon the state of the system, but merely upon the passage of the correct amount of time. So an example of a bound event is an arrival. Once an arrival has occurred at an event, the time of the next arrival can be scheduled by generating an inter-arrival time and adding it to the present value of that clock we mentioned. One of the entities in such a simulation could be an arrival generator, and the time attribute for this would just be the scheduled or bound time of the next arrival. So then once all the bound state changes have been made at an event, the simulation goes to step C, and it checks for every possible conditional state change that could occur at this event. So an example of this is start time or start service for a customer. It is conditional in the sense that it depends upon the state of the queuing being non-empty and on one of the servers being idle. So then once every conditional state has been checked and executed if it applies, the program goes through step C again because as a result of other state changes being made, others might be applicable, it might be possible for others to be executed as well. So the program repeats on step C until there can be no more state changes. And so that's kind of where we get the redundancy in the program. So for the GG1 queue, we have our entities of an arrival generator, a server, and individual customers. So we have a time attribute for the server. And so it's the time at which the next departure is scheduled. If the server is busy, then that duration of the service will be added to the time. If not, then the time is just set into infinity until the server moves to the busy state. So we can apply Little's formula here, which basically is that it's possible to dispense with a list of holding joining times for each customer, and the list would only be needed if the individual customer waiting times in the line or queue were required. Then our bound events for our queue is customer arrival and customer departure, and then we only have one conditional event of customer starts service. So then here is an algorithm that the book provided in Maple. That's their language that they use. And so it's an algorithm for simulating one cycle of the regenerative process. So a regenerative analysis will be performed of the simulation output data, which consists of the times at which the events take place and the line length immediately after each event, and the regeneration points are recognized, which are those at which the system enters the busy state from the idle and also an empty state. So the data collected is then used to estimate the mean L, which is the average number of customers in the system, and mean W, which is the average number of customers in the system times the average inter-arrival time. And that is the application of Little's law that we mentioned earlier. So now we have a simulation of a hospital ward, and this is just a list of all the variables that will go into that, which you can pause the video and go over those if you'd like, but we are going to have a hospital ward comprising of N beds, and we're going to suppose that our arrivals are coming in at a Poisson rate. And so this might be appropriate for a ward dealing solely with emergency admissions. And so patient occupancy durations are assumed to be a Weibull distribution. And so if an arriving patient finds all the beds to be occupied, the protocol kind of goes like this. If the time until the next scheduled departure is less than a specific threshold, then that patient leaves, and so they have an early departure, and the arriving patient is admitted to the momentarily vacant bed. Otherwise, that arriving patient cannot be admitted and is referred elsewhere. So we then use that three-phase A, B, and C steps. And so the bound events would be 1, an arrival, and 2, a normal scheduled departure. And so the conditional events are then that normal admission of the patient or early departure of the patient followed by the admission of the patient, and then lastly, that referral elsewhere of the arriving patient. So the simulation will be used to determine the proportion of patients referred and the long-run utilization of beds for the given arrival and service parameters given alpha. So with this, we wish to visualize this stationary steady state distribution of bed occupancy. And so that stationary distribution will exist for an arbitrary stationary arrival and service process times because the admission and discharge protocols ensure that there's never a queue. So for small wards, there will occasionally be times when all the beds are unoccupied, and so our regenerative analysis based upon this empty and idle states would be possible. However, if we had a much larger ward, even though the return to empty and idle times is certain, it may be so infrequent as to never occur within a lengthy simulation. So it's worth noting that if a ward were to be modeled to say Poisson closures due to infection, then these would provide convenient regeneration points. And so this is not included in this case. So the simulation for a given period of time is rather for a specific number of regeneration cycles. So the book gave us an example of using 20 beds in a ward, and they had a lambda of 25 per day. And so here is that input data that we can see that we use, and then it gives us that output statistics of the utilization and the proportion of the customers who get, or the patients who get referred somewhere else or actually allowed in. And so we can see here that we have a mean and standard deviations of patients' length of stay are 5.92 days and 2.53. So the 5.92 days is the mean and the 2.53 days is the standard deviation. And so we can also see that early departures are possible up to 1 day, so that's when alpha equals 1, prior to that scheduled departure times. So if interval estimates are required, then independent replications should be made in that usual way. The initial state of the ward is determined by the scheduled departure times for the beds occupied at time 0, and this kind of forms that part of the input data. So this might reflect the true state of the ward, in which case performing several replications of this simulation could show variability in that bed occupancy within that 10 days time. And so this is kind of used for short-term planning. But we can also see that, like usually, there's a burn-in period, and here it kind of looks like it's longer than necessary, but that's all to say that it's better to guess an initial state that might be more typical than that burn-in period. So this is the example in the book, and hopefully that helped just kind of provide a little bit of clarity of how to simulate that GG1 queuing system.